Okay, so I saying it because no, I just take it as granted as existing. So now we did a metric for vector fields and one forms, but we can expand the metric to we don't need that for wedge product of vector fields, but we need for wedge product of one form, so the whole exterior algebra. So let me write as definition. So let ng be a smooth Riemannian manifold. So start with Riemannian manifold. Okay, now what we have? This is the dimension of M. And then we have G from Xm times Xm to Fm and okay, I will write it in a simple way. And we also have G star from omega 1 m times omega 1 m to Fm to a smooth. So we have two forms and return a smooth function. We can expand this, so we can expand G star to all forms as follows. So as follows. So all forms. So we have G star P is from omega Pm times omega Pm to Fm, such that P is from 0 to D. And we have the following. G0, omega 0 are functions. Zero forms are functions. So J0 of, let's say, F1, F2 is F1 times F2. Here, these are functions. G1 is the same as the Hodge star. The G1 star of omega is G of omega at omega and eta are one forms. But for P forms, so for P at least 2, omega, I would do only for basis forms because for all other it's extended by linearity. Omega is no, I'll do directly. So G of omega. So let's take omega 1, omega p, eta 1, eta p, be one forms. Then G of omega 1 wedge omega p with eta 1 wedge to eta p is the following, is the determinant, this is G star p, is G star omega 1 eta 1, G star omega 1 eta p, and here G star omega p eta 1, G star omega 1 eta 1. Okay, this determinant gives the metric tensor on higher forms.
Down here, it should be G star. No.
So, but this is, so that I have to fix this as well. This is G star. Okay. Yeah. People usually use G for everything. But I want to be specific. I'll give some example maybe in 2D. Or let's do example in spherical coordinates. So let's say G2 star of d theta wedge d phi, d theta wedge d phi. So this is G star of d theta, G star of phi d theta d phi, G star of d phi d theta, and G star of d phi d phi. Okay, we had coefficient 1 before the theta, so this is 1. The theta and the phi there were no coefficients, mixed coefficients, so these are zeros. And here we had 1 over sine squared theta. This is 1 over sine squared theta. So the whole thing is 1 over sine squared. If I multiply this here, it will become it will become 1 there. So let me, we have also, I will write direct, so G squared theta of the theta wedge d phi, sorry, this is, let's write this, sine theta d theta wedge d phi, and sine theta d theta wedge d phi. Is that right? I'm confused a bit. It should be, this should be 1. Yes. Yes, so this is, now will be sine So this will be the first argument. Oh yeah. This is the same as G2 star. So this is the theta wedge sine theta d phi and the theta wedge sine theta d phi. And this will be now 1, then 0, then 0, and then we have sine squared theta over sine squared theta. So the d phi coefficients will be multiplied by sine squared now here, this one. And this will be, okay, let me write it in full because now it's a bit confusing. So this is G star d theta G star d theta sine theta d phi, G star sine theta d phi d theta, and G star of sine theta d phi sine theta d phi. And functions, they come outside. So this will be 1, 0, 0, and sine squared theta over sine squared theta, which is 1. Okay. Now, you have to, are you on the whole board or only this part? This is G1 star. Not G1, GP. It's P. Okay. So now we are ready to define a volume form. Let Mg be a Riemannian manifold. And this is the dimension of M. Okay. Now, so and then omega d of M is one dimensional. And G star D from omega dm times omega dm to F of M. And so we have this thing and this thing, and one-dimensional map. There exist two elements whose square is 1. So there exists, if any, because it could not, it's possible that there are no, but if any, two D-forms, and these are some kind omega and minus omega, or some omega. Such that G D star omega omega is 1. And any of these two D forms is called a volume form. And a volume form, it gives a volume form gives orientation, gives it is also it is an orientation form. So hence so if M is oriented, then there is a canonical choice of sign for the volume form. So there are two forms, but orientation gives one class, for example, which we call positive, and we take this in this class to be our volume form for the unique volume form that uniquely determines the volume form. We write vol maybe with respect to G, I don't know, and this is in omega D of M. So here, this form here is a volume form because we calculate that its square is 1. So for example, on RD, so this is the first one with D equal this integer. With the standard metric, G is dx1, which dx1 plus dxd, not which tensor product. On this, we have the volume form is plus or minus dx1 wedge to dxd. And 2 on the sphere on S2 in spherical coordinates. So this gives locally, spherical coordinates gives for the whole sphere, but not on the Greenwich meridian. So it's not a global form, but it can be extended to a global form. So on S2 in spherical coordinates, volume is sine theta d theta, which d phi. And we can compute volume forms if we know orthonormal basis. So we computed this form by checking that it satisfies the rule, but we can derive it. So we have the following proposition. So let Mg be an oriented Riemannian manifold. This is the dimension of M. And dx, so E1 to ED be a basis, an orthonormal basis of omega 1 such that E1 wedge to ED is an orientation, is in the same orientation class. The same. Okay, it's an orientation form. Is an orientation form. Not yeah, orientation. And this form is exactly the volume form. Then volume is this form. Now let's go from these examples. So first, if we have an RD with standard G, and standard orientation, dx1 to dxd is oriented, is an orthonormal basis. And hence volume is dx1 to dxd, which is this example one here. And second, on S squared in spherical coordinates, it was d theta and sine theta d phi is oriented is an orthonormal basis respecting the induced orientation. I will not check that, but respecting the induced orientation on S2. Induced from B, from the ball, from B1. Induced orientation on S2, and then therefore volume is d theta wedge sine theta d phi, which is sine theta d theta d phi, which we computed before. So this is the way you compute the basis, and then you compute the volume form by just multiplying the basis elements with their wedge product. Okay. Hodge Star maybe. Okay. The definition of Hodge Star. So let MG be an oriented Riemannian manifold of dimension D, and volume be its volume form. Be its volume form. Then the Hodge Star operator star P from omega P M to omega D minus P M, where P is from 0 to D, is the unique linear map. Linear. It is FM linear. It is linear with respect to functions, such that for any just will add a format to see what exactly. So I have G of omega star theta is omega. No, not this. People usually this. G of omega eta is omega times the volume form is omega which star theta. So we have star P. So omega is in omega P. Eta is in omega P as well. And we have here G star theta. And yes, we have this formula here. Now I will show a proposition that explains how to calculate Hodge stars, but this is the form.
Maybe if you write the Hodge star with the star and the pilot, yet distinguish it from the
Okay. Yes, this is star. Now I use some equivalent, not this equivalent formulation you not need it right now. Or maybe I will use it because it's important in the discrete case. It's not just this definition, but slightly modified definition of the next one. No, equivalently, okay, I have equivalently. It's not, it has to be proven, but let me just read it because I will make a mistake probably. Equivalently, um, for any omega in omega pm and eta in omega now d minus pm, we have g star d minus p star p omega eta with the volume form. So the difference is that we put now the Hodge star here, not here, is omega wedge at modified version of this will be used in the discrete case when we integrate that. Okay, now let's give a theorem. I will first write a theorem. So I will write two theorems at once. So let G be an oriented Riemannian manifold dimension D, and P is in 0 D. Then we have two things. First, so the second falls from the first. And okay, let's give. And E1 to ED is a positively oriented basis of orthonormal basis of omega 1. Then we have two things. First, if we have, I will write examples later. If E is a subset of 1D, has P elements, and define EI is by definition E of, so no, it's an ordered, it's ordered. So no, not this way. E is I1, IP, sorry, where 1 is less than I1, and let's make them in order, although for 3D we usually make a cyclic order. And EI is by definition EI1 wedge to EIA. And then if J1 to J D minus P is the complement of the ordered complement of I, Then and EJ is by definition EJ1 wedge to EJ. Then the star of EI, so the star of EI is some sign S times AJ, where S is in -1, such that AI wedge AJ is S times the volume form. So for example, we have indices 1, 2, 3, we get I is index 2 and J is index 1 and 3. And it will becomes E2 wedge E1 E3, and we have to rearrange to see what the sign is. S volume, which is S E1 to EG. This is the first part, and the second is proved from the first one. Okay, and the second is star D composed with star D minus P composed with star P is -1 to P times to the power D minus P of identity on omega P of M. In particular, when D is odd number, 3, this is always positive because you get, for example, 3 minus P times P if P is even, the whole is even. If P is odd, this is even. So in particular, when D is odd, star D minus P star P is identity, always, without any sign. Okay. Now let's give examples. So start with D equals 2, and E1, E2 is oriented, is an orthonormal. Okay, I will do the so consider an oriented orthonormal basis E1 to EG of some smooth manifold of some oriented MG. So this is oriented smooth Riemannian, and this is the dimension of M. I just want to not write everything. So now example 1. When you have 2D, D equals 2, then we have star 0 of 1 is E1 wedge E2, which is the volume form. Star 1 of E1 is E2, and star 1 of E2 is minus E1, and star 2 of the volume form, which is star 2 of E1 wedge E2 is 1. So in particular, so on a sphere with spherical coordinates, a few minutes to for 3D. We have star 0 of 1 is sine theta d theta wedge d phi, star 1 of, let's say, d theta is sine theta d phi. And now star 1 of sine theta d phi is minus d theta, which means that star 1 of only d phi is minus d theta over sine theta.
There is something weird here. You said when D is off, it's identity, but here when D is even, sorry, how is D?
Not P, yes. Well, it's not identity if both P and D are even. If D is even and P is odd, that is not identity. So this is D equals 2 and P equals 1. So star 1 of E1 is E2, but star of E2 is not E1, but is minus E1. And now let's write the 3D. And of course, I could not start physics. I'll start next time and mesh calculus. And example 2 now be the D equals 3, star 0. I don't have example here of non-standard metric, so it will be the same where EI is dxy will be for forms, for basis forms. So star 1 is E1 wedge E2 wedge E3, which is the volume form. Star 1 of E1 is E2 wedge E3. Why? Because E1 wedge E2 wedge E3 is a volume form. Star 1 of E2 is now E3 wedge E1. It is minus 1 E1 wedge E3, but we use cyclic coordinates. Star 2 of star 1 of E3 is E1 wedge E2. Star 2 of E2 wedge E3 is E1. So because it's the identity star of this is this, and again the rest. Star 2 of E3 wedge E1 is E2. Star 2 of E2 wedge E3 is E1, is E3, and star 2 E1 wedge E2 wedge E3 is 1. So this is start of the volume form. Start of the volume form, and this is 1. Okay. This one. This one. Yes. Now in R3 with standard metric, we have that EI is dxi, E from 1 to 3. So Here we don't have such strange cases like here. We have star of dx is dy dz, and star of dy is dz dx, and star of dz is dx dy, wedge dy. Okay, and that's how the Hodge star is computed. Usually, when in elementary introductions of Hodge star, it's shown only this, but I wanted to show how it's done for non-Euclidean metric. So here we have to be careful. The basis is not d theta d phi, but d theta and sine theta d phi. So the calculation is different. Okay. Any questions?
So, the discrete calculus.